sac201 number 3. It's a Coulomb's law problem. I'll give you a chance to read it. Probably want to pause here if you want to read it thoroughly, but we've got 3 particles, and we're supposed to find the net force exerted on particle number 3 by the other 2. So these 2 are going to be exerters of the force, and number 3, the victim. I've already started this one. By creating the necessary sketch here. Particle 1 at minus 4.5 centimeters, 0. Here's the XY coordinate system, the origin right here. So over 4.5 and up 0. Particle number 2 over 0 and down 10.6 centimeters. And particle 3 over 6.80 centimeters and up 0. In applying Coulomb's law, what matters, with this one being the victim, is its distance from here, which I've indicated as R1, and its distance from particle number 2, which I've indicated as R2. R1 we can calculate as this distance, x1, plus this distance, which I've labeled x3, which is 4.5 centimeters plus 6.8 centimeters. And that adds up to 11.3 centimeters. In SI units, 0.113 meters. So I need that value. R2 I can get using Pythagorean theorem. It'll be the square root of the square of x3 and y2. Let's go ahead and get that. R2, that's the distance that charged particle number 3 is from particle number 2, is x3 squared plus y2 squared, all raised to the 1/2, and take the square root of that. So 6.8 centimeters squared plus 10.6 centimeters squared, make the square root of it, and for R2 I get 12.59 centimeters, or 0.1259 meters. Values were all given to 3 sig figs. So I want to get the answer. Even that one was actually 6.80 centimeters. Get the answer to 3 sig figs. To do that, I'll carry 4 sig figs in the intermediate results. Okay, now I'm in a position to calculate the force on particle number 3 due to number 1. I'll apply Coulomb's law in order to get that. Let's call it F1, and it's going to be K Q1 Q2 all divided by R1 squared, and that's 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times Q1 which is 0.85 times 10 to the minus 6 coulombs. It was given as 0.85. It is just two sig figs. 0.85 microcoulombs, and micro means times 10 to the minus 6. And then Q2, it's actually Q3 in this case. Force of particle 1 on number 3. And that's given as 1.4 times 10 to the minus 6 coulombs. And all divided by the R1 squared. We just found R1 to be 0.113 meters. That's the distance from that particle 1 is from particle 3. So we're now calculating the force of 1 on 3. I'll go ahead and depict that. I'm calling that F1. So we're finding the magnitude of F1 at this point. And if you go ahead and evaluate that, you get 0.8378 newtons. For F1. Alright. Now we got to get F2. F2 is the force exerted by particle number 2 on particle number 3. Up in this direction. Call that F2. Subscript 2 on it. F2. I'm going to make K Q1, I should say K Q2, Q3 over R2 squared. Q2 there, Q3, that was 1.4 times 10 to the minus 6 coulombs, and then I'm going to need the separation between 2 and 3. So particle number 2 had a charge of 2.05 times 10 to the minus 6 coulombs. And the separation, the R2, we found to be 0.1259 meters right there. And that evaluates to 1.628 newtons. F2. Okay, so now I've got values for both F1 and F2. I need to add those two together like vectors. I'm going to do a component diagram for F1. Actually going to be a pretty simple component diagram for F1. Let's try doing that over here. No, I think I'll continue on down the page. But that is an easy one. It's got an X component and a Y component. Breaking that up into components, no big deal. Component diagram for F2, get the X and Y components of F2. I am going to need this angle in here. Let's go ahead and find that angle. Go switch colors for you. So this angle right in here, call it theta. I can say the tangent of theta is the opposite over the adjacent. So tan theta is equal to y2 over x3, or the arctangent, or I should say the angle itself is the arctangent of y2 over x3, which is the arctangent of 10.6 centimeters divided by 6.80 centimeters and that works out to be 57.32 degrees. Alright, that's our angle that force F2 makes with the horizontal. That'll be this angle right here as well. Alright, let's start breaking these forces up into components. Draw the vector component diagram for F1. Here's F1. F1x is equal to, well, F1 itself was 0.8378 newtons. So F1x is 0.8378 newtons, and F1y is equal to 0. And then the other one's more interesting. It is F2 up here at an angle theta, which we found to be 57.32 degrees. Decimal point right there. There's F2x, F2y. Let's see, F2x over F2 would be adjacent to that angle over the hypotenuse. So that would be the cosine of theta. Or F2x is equal to F2 cosine of theta. So F2x is F2 we found to be 1.628 newtons. And then times the cosine of that, 57.32 degrees. So F2x is equal to, I get 0.8790 newtons. Need that. F2y is the opposite to the angle. Divide that by the hypotenuse. Opposite over hypotenuse is the sine of the angle. So I got F2y is F2 sine of theta. Again, F2 is the 1.628 newtons. So I got F2y is 1.628 newtons times the sine of 57.32 degrees. And I need these two values as well. I'm ready to add the two vectors, F1 and F2, to get the total force on particle number 3. I'll just call that F, and its x component is going to be F1x plus F2x, which is the 0.8378 newtons that we've got up here. Plus the 0.8790. So the x component of the force on particle number 3 is, I get 1.717 newtons. Then the y component, F1y plus F2y, that's 0 plus, looks like I never finished evaluating that. F2y is actually 1.370 newtons. So this is the thing I actually wanted to circle as opposed to this guy. Alright. 1.370 newtons. So Fy itself is just the 1.37 newtons. Now we got to take the components of our answer vector and put them together to get the actual answer vector, that is, the force on particle number 3 exerted by a combination of the force of particle number 1 on it and a force of particle number 2 on it. So we'll draw a little vector component diagram to put it together. Let's see, got the coordinate system looking like that. Here's the Fx. Being equal to 1.717 newtons plus Fy of 1.370 newtons. They all add up to F itself, which is going to be at some angle. I'll call it phi since I used up the symbol theta before. So F itself by Pythagorean theorem is going to be this side squared plus that side squared all raised to the 1/2, or F equals Fx squared plus Fy squared square root. That'll give me the magnitude of it. That's 1.717. plus the Fy, 1.37 newtons. All squared, take the square root of that, and I get, for the magnitude of the force, 2.20 newtons, rounded to 3 sig figs. And then for the angle, let's see, the tangent of phi would be opposite over adjacent. So tangent of phi equals Fy over Fx. So phi itself is the arctangent of Fy over Fx, or phi is arctangent of 1.37 newtons divided by 1.717 newtons. So phi is, evaluate that, I get 38.6 degrees. 3 sig figs. So the final answer is F vector is equal to 2.20 newtons at an angle of 38.6 degrees above the positive x direction, or counterclockwise from the positive x direction. And that's our answer.